Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The astonishing story of gravitational waves. The universe is not silent. It hums and vibrates with a symphony composed by the most massive and energetic events since the dawn of time. This celestial orchestra does not play with sound as we know it, but with ripples in the very fabric of spacetime itself. Gravitational waves. These waves, predicted over a century ago by Albert Einstein in his theory of general relativity, have opened a new window into the cosmos, allowing us to hear the universe in a way never before possible. In 1915, Albert Einstein revolutionized our understanding of gravity with his general theory of relativity. Instead of viewing gravity as a force between masses, Einstein described it as a curvature of spacetime caused by mass and energy. Objects like planets and stars warp the spacetime around them, much like a heavy ball placed on a trampoline stretches the fabric. Smaller objects move along the curves created by these distortions, which we perceive as gravitational attraction. One of the most startling predictions of general relativity was that massive objects in motion, such as orbiting black holes or neutron stars, could create ripples in spacetime that travel outward at the speed of light. These ripples, or gravitational waves, would carry energy away from the system, causing the orbiting objects to slowly spiral inward. However, the effects of gravitational waves were so subtle that Einstein himself doubted we would ever detect them directly. For decades, gravitational waves remained a theoretical curiosity. The technology needed to detect these incredibly faint signals did not exist, and the waves themselves were so weak that even the most violent astrophysical events would produce only minute disturbances by the time they reached Earth. The challenge was immense. Detecting a change in distance on the order of a fraction of the diameter of a proton over kilometers of space. In the 1960s and 1970s, scientists like Joseph Weber began the first serious attempts to detect gravitational waves. Weber's work involved massive, cylindrical aluminum bars that would resonate if a gravitational wave passed through them. Despite initial claims of success, his results could not be replicated, and skepticism grew. The breakthrough came with the advent of laser interferometry. This technique, which uses lasers to measure extremely small changes in distance, offered the precision needed to detect gravitational waves. The concept was simple yet ingenious. Split a laser beam into two perpendicular arms, bounce the beams back and forth between mirrors at the ends of these arms, and then recombine them. A passing gravitational wave would stretch one arm while compressing the other, creating an interference pattern that could be measured. The birth of LIGO. The Laser Interferometer Gravitational Wave Observatory, LIGO, was conceived in the late 1980s as a collaboration between MIT, Caltech, and other institutions. Funded by the National Science Foundation, LIGO consisted of two massive facilities in Hanford, Washington, and Livingston, Louisiana. each with two 4-kilometer-long arms. After years of development and refinement, LIGO began operations in the early 2000s but initially failed to detect any gravitational waves. The project underwent significant upgrades between 2010 and 2015, increasing its sensitivity by a factor of 10. This new incarnation, known as Advanced LIGO, began its first observation run in September 2015. Just days after turning on, LIGO made history. On September 14, 2015, the LIGO detectors in Hanford and Livingston simultaneously registered a signal. The characteristic chirp matched the predicted signature of two black holes spiraling inward and merging, a phenomenon that had never been directly observed. The black holes, with masses of 29 and 36 times that of the Sun, collided roughly 1.3 billion light-years away, releasing more energy in a fraction of a second than all the stars in the observable universe combined. This landmark discovery, announced on February 11, 2016, confirmed a major prediction of general relativity and opened a new era of astronomy. For the first time, humanity had detected gravitational waves, directly observing an event that occurred over 1 billion years ago. The universe, it seemed, had begun to speak to us in a new language. The discovery of gravitational waves transformed our ability to study the universe. Traditional astronomy relies on electromagnetic radiation, light, radio waves, X-rays, etc., to observe celestial objects. However, much of the universe is hidden from view in this spectrum. Black holes, for example, do not emit light, making them invisible to traditional telescopes. Gravitational waves, on the other hand, are emitted by massive objects in motion, regardless of whether they produce light. This allows us to observe phenomena that were previously beyond our reach. One of the most exciting aspects of gravitational wave astronomy is its ability to observe black hole mergers. These cataclysmic events occur when two black holes, locked in a death spiral, collide and merge into a single, larger black hole. The waves produced by these events encode information about the masses and spins of the black holes, providing insights into their origins and the environments in which they formed. Since the first detection in 2015, LIGO and its European counterpart, Virgo, have observed dozens of black hole mergers. Each detection adds a piece to the puzzle of black hole formation and evolution. For instance, by studying the distribution of black hole masses, astronomers can infer details about the stars that gave birth to them and the processes that led to their formation. Gravitational waves also allow us to observe neutron star mergers. Neutron stars are the remnants of massive stars that have exploded as supernovae. They are incredibly dense, with a mass greater than the Sun packed into a sphere only about 20 kilometers across. When two neutron stars merge, the resulting event is spectacular, producing both gravitational waves and electromagnetic radiation. In August 2017, LIGO and Virgo detected a signal from the merger of two neutron stars, located about 130 million light-years away. This event, named GW170817, was accompanied by a burst of gamma rays and followed by a kilonova, an explosion that occurs when neutron-rich material is ejected from the merger and undergoes rapid neutron capture, producing heavy elements like gold and platinum. This multi-messenger observation confirmed that neutron star mergers are a primary source of these elements, providing a key piece of the puzzle in understanding the chemical evolution of the universe. Gravitational waves also offer a unique way to probe the early universe. Shortly after the Big Bang, the universe underwent a period of rapid expansion known as inflation. This process should have produced primordial gravitational waves, which would still be present in the universe today. By detecting these ancient waves, we could gain direct insight into the conditions of the early universe and the fundamental physics that govern its evolution. Current detectors like LIGO and Virgo are not sensitive enough to detect these primordial waves, but future observatories, such as the planned space-based Laser Interferometer Space Antenna, LISA, may be able to. LISA, with its constellation of satellites forming an enormous interferometer, will be capable of detecting lower-frequency gravitational waves, opening up a new frontier in our exploration of the cosmos. Gravitational waves also hold promise for improving our understanding of cosmology. One of the most important parameters in cosmology is the Hubble constant, which describes the rate at which the universe is expanding. Traditional methods of measuring the Hubble constant have led to a discrepancy between values obtained from observations of the early universe and those based on observations of the local universe. Gravitational wave observations offer an independent method for measuring the Hubble constant. By detecting the gravitational waves from a binary neutron star merger and identifying the host galaxy, astronomers can determine the distance to the event and compare it to the redshift of the host galaxy. This standard siren method has the potential to resolve the discrepancy in the Hubble constant and provide a more accurate measure of the universe's expansion rate. The field of gravitational wave astronomy is still in its infancy, but its potential is enormous. As detectors become more sensitive, we will be able to detect more events and probe deeper into the universe. New observatories, such as the aforementioned LISA, the Japanese Kagra detector, and the proposed Einstein telescope, will expand our capabilities and allow us to explore new frequency ranges. These advancements will enable us to study a wider variety of astrophysical phenomena, from the mergers of black holes and neutron stars to the vibrations of rotating neutron stars, known as pulsars, and even the possible existence of exotic objects like boson stars or primordial black holes. Each new detection will provide more data to test our theories of gravity and the behavior of matter under extreme conditions. Gravitational waves have opened a new window on the universe, allowing us to observe some of the most violent and energetic events in the cosmos. From the first detection of colliding black holes to the multi-messenger observation of neutron star mergers, these ripples in spacetime have revolutionized our understanding of the universe and its fundamental processes. As we continue to listen to the symphony of the cosmos, gravitational waves will undoubtedly reveal more secrets and deepen our understanding of the universe. The era of gravitational wave astronomy has just begun, and its future promises to be as dynamic and transformative as the waves themselves. Through this new lens, we will explore the hidden corners of the cosmos, uncovering the mysteries of its most enigmatic and powerful events, and continuing humanity's quest to understand the universe in which we live.